Okay, so today we talk about section 3.3. This is where we talk about the average rate of change. And since we'll be using this a lot, let's just abbreviate this to AROC, okay, the average rate of change, and the behavior of graphs. Okay, so let's look at this chart. Okay. Now, what this chart is it's the cost of a gallon of gasoline for every year. So in 2005, the cost was $2.31. In 2006, $2.62, etc., 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 etc. Okay? And we can see that the function's increasing. Okay? Every year, the gas is going up. In 2009, it does go down, but then it comes back up again, up and up. So we could ask ourselves, how much did it increase in 1 year? Well, from 2005 to 2006, it increases 31 cents. That is, if I take $2.62 and subtract $2.31, that's 31 cents. And the difference between here is 1 year. So in 1 year, it changed 31 cents. Okay. Now over here, we could look and do the subtraction. 284 minus 262 is 22 cents. Okay. So in that year, it increased 22 cents. So it's not increasing at the same rate. We could ask ourselves, okay, well, from this year to this year, there's 2 years in between there, how much on average did the gas go up? Okay. To do that, we'd have to take $2.84 and we could subtract $2.31 to get 53 cents. Okay. But then we'd have to divide that by 2 to find out how much on average it changed during that time. Okay. We could do the same thing here. Now, here's 1 year, 2 years, 3 years. We could take this amount, subtract this amount. Okay, so that would be almost $1, so 99 cents. Okay. And now we would be dividing by 3. So it would be 33 cents a year on average that it changed those 3 years. So really what we're saying is, we're going to be working with this and this, when we're looking for this average rates of change, okay, if we're looking at the price now, let's look at it between 2005 and 2012. So in 2005, the cost of that year, the gas that year, it was $2.31, and in 2012, it was $3.68. So what we were really doing is that we were looking for our average rate of change, and we said that that was really the change in the output here, the change in the cost of gas. And we were dividing it by the change in the input, which was the number of years. So time is always your independent variable. So these are also, remember, outputs are known as dependent variables. Remember, dependent variables usually are denoted by y. In this case, we have this as a C of y, meaning years. Okay, I prefer really that let's call it t, so we don't get ourselves confused. Okay, And then the independent variables are usually x's, okay, or t's if you have them. Okay. So we'll use the x's and y's as I go through this. So the change in the output is really the change in the y's over the change in the x's. And it gets tedious to keep writing change in out, so a lot of times you'll see this notation. It's a delta. It means the change in y over the change in the x. And now we've seen this before. A change in y's we often write as y2 minus y1, and the change in the x we often write as x2 minus x1. And remember the y's, well, because now we know about functions, y2 is really just the function evaluated at x2. And then we subtract off y1, but remember that's just the function evaluated at x1. Divided by x2 minus x1. And it's probably most familiar to us in this form, but all of this, the average rate of change, what we're talking about, is really just slope between 2 points. So if we want to know the average rate of change between 2005 and 2002, or 12, I'm sorry, this is really our x2, and this is our x1, and this is our function evaluated at x1, or our y1, and this is our function evaluated at x2, which is also the y2. So our average rate of change here would have to be f of x2 minus f of x1 divided by x2 over x1, which in this case, f of x2 is $3.68. We subtract off the $2.31, and then x2 is 2012 minus 2005. Alright, now let's do that subtraction. I'm going to have to move down here, or over here, I can do it. So that's equal to 8 minus 1 is 7, 6 minus 3 is 3, 3 minus 2 is 1. $1.37 divided by 12 minus 5 is 7. So this would be the exact average rate of change. Approximately, it's 19, well, 20 cents, okay, give or take. That was an approximation of the average. Okay, let's try one more. Now on that table, there was one year that it decreased. In 2000, well, it decreased a couple times. Okay, so 2007, the price is $2.84, and in 2009, the price was $2.41. I'll give you a minute. Can you determine the average rate of change of the gasoline between these 2 years? So if 2007 is x1 and 2009 is x2, this is the function evaluated at x1, this is the function evaluated at x2. Okay, so f of x2 is $2.41, and we're going to subtract off the function evaluated at x1, which is $2.84, and divide that by x2, which is 2009, divided by, subtracting off 2007. So in our denominator, we simply have 2. For here, $2.84 minus $2.41. There was a change of 43 cents, but we're subtracting off a larger number, so we're actually subtracting negative 43 cents. Okay. And that's going to be approximately, it decreased 22 cents. Alright, so that's how you determine average rate of change from a table. The question is, how do we do it now from a graph? So let's say our graph looks like so. You put some points on here. This is 0, 1. This is 1, 0. This is the point negative 1, 4. 1 we have 0 and at 2 we also have 1. May as well put one more up here. At 3, the function value is 4. Okay. So remember, these are the x's. This is the f of x. Okay. And so all of these ordered pairs I've written down really come in the form x, comma, f of x. Okay. So remember, y is f of x. All right. So here's our graph. Now, if we want to know the average rate of change, we have to know from where to where. Okay? We have to have a start point and an end point. So we want the average rate of change on the interval negative 1 to 2. So this is interval notation. These are our x values. So what that means is that this is x1 and this is x2. So if I come up to the graph then, if x1 is negative 1, then f of negative 1, or f of x1, is 4. Now x2 is 2, so that means here 1 is f of 2 or f of x2. Okay, so when I put x2 in, which is 2, out comes 1. So 1 is our f of x2. Okay, so now we can do it. We're just looking for this average rate of change, which is the slope. It is the slope of this line, okay, that goes through the graph. I hope it's clear that this graph is not changing at a constant rate. Down here, it's in what we'll talk about later is increasing, but it's increasing much slower than, say, up here. Here we're taking off to infinity. Here it's decreasing much more rapidly as it slows down here. So there's a change in the graph that is different at every single point, so we're just wondering about the average in between negative 1 and 2. Okay, so here we go. Slope is the average rate of change. Okay. It is the function evaluated at x2 minus the function evaluated at x1 divided by x2 minus x1. Well, f of x2 we said was 1. Then we put a minus in from the formula. And f of x1 is 4. And then we divide that by x2, which is 2. And then we have a minus from the formula. And x1 is negative 1. Now we can just subtract. 1 minus 4 is negative 3. These become positive, so 2 plus 1 is 3. So the average rate of change here is 1. Negative 1, sorry. And that makes sense because, as we'll talk about, this line has a negative slope. It is decreasing. Okay? So this should be negative as well. So that's a specific example of how we do it using a graph. Let's try and do it in general. So if we're given any curve, we could figure it out. Okay, so let's say I have some curve. Say it looks like this. Okay. I don't even know what this function value is. It is a function though. It'll pass the vertical line. So this will be our f of x. This will represent the function values, these represent the x values. Now let's say I want to pick a point on here. Then we know this ordered pair is x, and then whatever that function value comes out to be. That means down here this value is x. So that'll be our starting point. Now I want to look at how the graph will change from our starting point to an ending point. And I don't want to be specific about that ending point. Let's say I just want that ending point to be some distance away, and let's call it h. Okay. H means I could vary it. I could make it smaller or larger. Okay, so we're just doing this in general, so we'll call this h. So when I finish, this point here must be this distance x plus the distance h that I chose to have gone. Then there is a point on this graph where the x value is x plus h, and the y value has to be the function evaluated there. So if we're looking for the average rate of change, we'll be looking for the slope of the line that goes through there. Okay, so now let's try and do it. Okay. Remember, average rate of change is equal to the slope, which is their function evaluated at x2 minus the function evaluated at x1 over x2 minus x1. So now the question becomes, well, what's our x2 and what's our x1? Okay. We will let this be x2 because it's further down the x-axis, and we can let this one equal our x1. So that will make this equal to our function evaluated at x1, and this one will become the function evaluated at x2. That's what we're going to substitute in here. Okay, so let's do that. The function evaluated at x2 is f of x plus h. Then we'll subtract off from the formula. I don't know if this way it'll help. Then we're going to subtract off f of x1, which we see here. F of x1 is just f of x. Then we can divide by x2, which is x plus h, and then we'll subtract off from the formula x1, which is just x. Now, we can't simplify the numerator because we don't know what the function evaluated at x plus h is, nor do we even know what the original function is. But we can simplify this denominator because if I take x and I subtract off x, I'll just be left with h. And I hope this looks familiar to you. We did some work with it last time. This is what is known as your difference, because there's a subtraction, so a subtraction known as a difference, and then the quotient. A quotient because there's a division. So let's try and work with this difference quotient specifically. Alright, so for example, if g of x is equal to x squared plus 2x minus 4, we want to find and simplify the difference quotient. Okay, so when you're asked to do the difference quotient, remember that's going from x to x plus h. That's what we just found out. So in our case, we'll be taking g and evaluating it at x plus h, then subtracting off g, the original function of x, and then dividing that whole thing by h. Okay, so here we go. Now, the function evaluated at x plus h, g is something squared plus 2 times that something minus 4. That's the form of g of x. So if I'm evaluating it x plus h, I put in x plus h is there. Now I'm going to subtract off the original function, which we have here, but this is a polynomial, so remember we've got to open up parentheses. So this is, I'll put it in blue. And then we can divide this whole thing by h. Okay, so let's be careful about what this means. Remember, this is x plus h times x plus h. So what I'm going to do now is start expanding this so I can collect any like terms so I can simplify it. Okay. Then I'm going to distribute this 2 through. So 2x's plus 2h's, and then minus 4. So all of this is g of x plus h. Just doing some manipulation with it. Okay. Now here, I want to be careful and distribute. So this is minus x squared minus 2x plus 4. And then all of that is still divided by h. But there's still some more work to do. Let's FOIL this out. This would be x squared plus xh plus hx. And remember, multiplication commutes, so this is just 2xh plus h squared. And then I'm just going to copy the rest. Okay. Alright, now I'm going to combine like terms. Okay? And here's where the magic happens. Here I have an x squared, and there I have a minus x squared. Here I have 2 x's, and I'm subtracting off 2 x's. Here I have minus 4, and here I'm adding 4. So what I'm left with is 2xh plus h squared plus 2h, and all of that is divided by h. And we can simplify that further. Since this is a single term in the denominator, this is the same as the first term over the denominator, plus the second term over the denominator, plus the last term over the denominator. And now we can see canceling happen. Here I have two h's up top, so I'm left with one. So in the end, there's just two x's plus this h plus this 2. Alright, let's do a more difficult one. This is going to have to cause us to remember how to work with fractions. Let's say our function is 2 over x plus 5, and we want to find the difference quotient. Okay. So first let's write down what that would be. So the difference quotient is f of x plus h, then we subtract off f of x, and we divide that whole thing by h. So let's write that out. Okay. So f of x plus h is 2 over, now not just x plus h, okay, plus 5. Okay. So this is f of x plus h. Now we're going to subtract from the function, and we subtract off the original function, which is just evaluated at h. Or I'm sorry, at x, and then we'll divide that whole thing by h. Now the goal is the same here. We need to simplify this numerator. Okay. And when we do it, we'll be subtracting fractions. And so to subtract fractions, we need a common denominator. Now what you might be tempted to do is say, well, this one just has a plus h, so I'm going to add h here and here. But remember, that's not how we find common denominators. We find common denominators through multiplication. Okay. So our least common denominator is the multiplication of the two. So what I'm missing over here, I have the x plus h plus 5. I need the x plus 5. And I have to do that up top and down below. Now over here, I am missing the x plus h plus 5. So that's what I have to multiply by on the top and the bottom. Okay, and now we're prepared to do this. Okay. First of all, before I move this, because we already have fractions to deal with, okay, I have the numerator being divided by h. Okay, so if I was to divide this, I would have to flip it over and multiply. Okay, and then I would be multiplying by 1 plus h, or 1 over h. So let's just do that now, so we won't have to deal with the complex fraction. Okay, so 1 over h is coming out. Okay. Now I'm going to simplify this. Okay. So we've decided the common denominator is x plus h plus 5 over x plus 5, or times x plus 5. Okay. The first term is this, 2 times x plus 5. And then here, don't forget about this negative, we have minus 2 times x plus h plus 5. So that's just the first numerator minus the second numerator. Okay, so now let's simplify. 1 over h will stay the same, and the denominator will stay the same as well. Do not multiply this thing out. Okay, we're going to hope for canceling. So don't multiply it out. And then here we can distribute to get 2x's plus 10. And here we have to distribute not just the 2, but the negative 2 through everything. So now we can collect like terms. And again, we'll have a lot of nice things happen for us. Here's 2x's subtracting 2x's. Here's 10 subtracting 10. So the only thing we have left is negative 2h. Okay. The 1 over h is still outside here. Over x plus h plus 5 times x plus 5. And there's one last bit of canceling that we can do. Here we have an h and here we have an h. So in the end, it's just negative 2 over x plus h plus 5 times x plus 5. Okay, so those two are as hard as it's going to get. Let's look at some other ways we could do it. Okay. Let's say our function is f of x is equal to x minus 2 square roots of x, and we want to do it on the interval from 1 to 9. We're looking for that difference quotient. So when it's written like this, remember this is your x1 and this is your x2. Let me write that one in green. Okay. So the difference quotient says you'll take f of x2 and subtract off f of x1 and divide that by x2 minus x1. Okay, well, what is f of x2? Well, x2 is 9, okay, so we're going to find that. So in the function, wherever we see an x, we put in 9. Okay, so this is f of x2. Now we're going to subtract off the function evaluated at 1, but remember this has got multiple terms, so we're going to open up the parentheses. And so this becomes 1 minus 2 times the square root of 1. So this is f of x2, or f of x1, sorry. And let's see, so we're subtracting x1, x2 is 9. Alright, now let's evaluate that. That becomes 9 minus 2 times, well, the square root of 9 is 3. Then we subtract off 1 minus 2, and the square root of 1 is 1. Over 8. Now we can simplify. So this is 9 minus 6 minus, inside of here we have 1 minus 2, which is minus 1, over 8. Here we have 9 minus 3, and then plus 1 over 8, which is 4 over 8, which is 1/2. Okay, we could also do it, so this is the difference quotient with numbers. We could also do it on an interval that's unknown. We could do, what should we do? Let's let our function be f of x is equal to x squared plus 2x minus 8. And let's do it on the interval from 5 to some unknown value after that. This is the number 5. Okay, and we're looking for the difference quotient, so this will be x1, this will be our x2. And the difference quotient says you take f of x2 and you subtract off f of x1 over x2 minus x1. So f of x2, I'm going to take the function and evaluate it at a. Then x1 is 5, so f of x1 is f of 5 over x2, which is a, minus x1, which is 5. Now I actually have to evaluate and find what f of a is. Well, if f of x is x squared, then I'm just going to do a change in variables. F of a is a squared plus 2a minus 8. And then I'm going to subtract off the function evaluated at 5, which is 5 squared plus 2 times 5 minus 8. All over a minus 5. Okay, so let's evaluate this. This is 25 plus 10 minus 8. 10 minus 8 is 2. 25 plus 2 is 27. Okay. So just copying now. We have a squared plus 2a minus 8. And now I have to subtract that 27 over a minus 5. This is a squared plus 2a minus 35 over a minus 5. But there was some canceling that occurred in the other difference quotients, so I highly suspect that there is some here. Let's factor this. This will factor into a minus 5 and a plus 7. And divide this by a minus 5. And you can think about this as a minus 5 times 1 if you want, it doesn't matter. It might help you see what I'm about to do next, because then these two will cancel, and we're left then with just the a plus 7. Okay, so the difference quotient is going to take a little bit of work and some good bookkeeping skills. Allow enough paper on your homework to do this so you can keep track of all the negatives. Don't forget to distribute this negative through. Now let's talk about the behavior of graphs. I talked earlier about being increasing or decreasing. Alright, so if I was to draw a function like this for you, let's say this is the point 2 comma negative 16, and this is the point negative 2 comma 16. The graph changes its behavior as it's going. if I follow along from negative infinity to infinity in the domain of this graph, so as x is coming this direction, the function is actually, what we call it increasing. Okay, so you can imagine that if you were walking on this, you would be walking up. So this is an increasing function, and it increases up until that value in the domain of -2, and at -2 it stops increasing. And in fact, at this point, it's neither increasing nor decreasing, because for a split second, it's just hanging in the air. You could imagine a ball for gravity. And then after this value in the domain, the graph starts decreasing. Okay, so you could imagine then that you are walking down. And so this is a decreasing function. But it doesn't continue to decrease. It decreases and decreases, and it slows up until this point in the domain, which is +2. And then the graph starts increasing again. So you'd be walking back uphill. And this is increasing. Okay. Now, what we're talking about in these values, then we said we were increasing from negative infinity all the way up to -2. We were increasing here to here. And then we also said we were increasing from here to here again. This time it starts at -2 and it goes to infinity. These were increasing. In between here and here, so that is in between -2 and 2, the function decreased. Okay. Now, let's think, I want to give you the technical definition of this. Okay? So, I need some pens. Okay. Let's say I pick a point on here A and a point in here B. Okay. Then if I come up here, this is the point B, comma, the function evaluated at B. Okay. I don't know what it is. If I come down here to A, this is the point A and the function evaluated at A. Well, what can I say about these things for sure, even though I don't know what f of A and f of B are? Well, if it's an increasing function, I know that f of B must be greater than f of A. That is, if I'm to increase, f of B will be above f of A. Okay. But we have to say when that's going to happen. And that happens when B is bigger than A. So this is a definition for increasing. Okay, I have this condition here. I have B is greater than A. Okay. So it is less negative, therefore it is greater. And the function evaluated at B is greater than the function evaluated at A. Okay, let's see if that holds true if I pick an A and a B in here. Okay. So now, we do have the same condition. We have B is greater than A. That is true. Now let's see what happens to the function values. Okay. So, looks like this point here is A, comma, the function evaluated at A. And down here, This is the point B and the function evaluated at B. So now if we look at f of B and we compare that to f of A, it's no longer true that f of B is greater. Okay? Down here, f of B is in the negative values. Up here, f of A is positive, so it's no longer true. So in the decreasing function, we have that f of B must be less than f of A. This is decreasing. This is increasing. And let's see if our definition holds up here as well. And let's pick an A and a B. We've picked them so B is greater than A. And let's see about the function values. So here is the point A now and the function evaluated at A. And up here we have B and the function evaluated at B. So how is it that f of B compares to f of A? In this case, f of B, if the function is increasing, is again greater. And that is what we said over here. So this is the intuitive understanding walking up and down of the graph. This is our technical definitions of what it means to be increasing. And notice that when we talked about the intervals that it increased on, we answered in the domain values from negative infinity to 2 and from 2 to infinity. And the same with the decreasing. Okay? So that's how you answer these questions. You look at what the function's doing, but you answer for the values of x. So let's try a different one. Okay. We'll come back to this diagram. Okay, so let's say I have some graph that looks like this. It's giving you some points. Let's say this is 1, negative 1, and that this is the point 3, 1, and that this is the point 4, I don't know, let's make this make it easier on ourselves. Let's make this 3, 2 and make this 4, 1. Okay. So this is our function. We don't know what it is. Okay. Can you find the intervals of increasing and the intervals of decreasing? Okay, so here you can imagine that I would be walking down or sliding down a hill. So from here to here, this function decreases. So that interval starts at negative infinity and goes up to the domain value of 1. By the way, intervals of increasing and decreasing never get brackets. Now after this point, I would be walking back uphill. So for these domain values, I would be increasing. And those domain values go from 1 to 3. After that point in time again, I'd be sliding back down. So I'd be decreasing. Okay. So I have yet another interval of decreasing, and the domain values for that are 3 to 4. After that point in time, I would start increasing again. So that interval goes from here to here. This is increasing. And it goes from 4 to infinity. Okay, so that's all you have to remember when you're answering these. Remember, answer. I think the increasing and decreasing most students are okay with. We just have to remember how to answer them with the domain values. So notice really what we had here, that we were okay till this point, and then the point graph turns, and then the graph turned again, and then the graph turned again. So these are known as turning points. And turning points will also be where local minimums and maximums happen. Okay. Now, as an absolute maximum, this graph continues to infinity. Its range, let's see, what's this lowest value here, is -1. It includes -1 and goes to infinity. Okay, so it has, well, let's talk about this. It has an absolute minimum here of -1 at x equals 1. On the other hand, there is no absolute maximum because the function will go on forever. Okay, so we don't ever say infinity is an absolute maximum. But if we just examine this graph on smaller areas, these turning points are certainly important. So if I just look at a local or a relative area, this turning point here provides a local minimum. In that area, we have a local minimum of -1, also at x equals 1. Okay. So it's perfectly okay to have your absolute an absolute minimum and an local or relative minimum be at the same point. And if we just look at this area as well, in this area of the domain, this is a local or a relative minimum as well. So we have a relative or local minimum of 1 at x equals 4. This turning point is also important. Just in this area, it provides a relative or a local maximum. Okay, so if we're just looking at that, we have a relative or local maximum of 2 at x equals 3. I hope that makes sense. And so one thing we should note, this will become important later on as we get to calculus and throughout. So let's say we have a graph that does this, and we have one that does this. Here we have a point, and here we have a point. Okay. Doesn't matter what we call them, x1, xy, x1, y1, doesn't matter. Okay. And we'll say they'll continue on to infinity. This graph has a maximum. It'll be both local and absolute. The value of the domain here is x. And what we should notice then is from negative infinity through to this value of x, this function is increasing. Now on the other side, we'd be sliding down. So from x to positive infinity, this function is decreasing. And this will just have to happen if you're going to have a maximum. You're going to have to first increase, which means we'll have positive slopes, and then we will have to decrease, which means we'll have negative slopes here, if we were to look at average rate of change. Okay. Alternatively, here we have some x1. This graph has a minimum, both a local and an absolute. And now, from negative infinity up until this value of x1, this is a decreasing function. And then after that turning point to infinity, the graph changes directions and it increases after that point. And so that will be a defining feature of graphs with minimums. You're going to have to decrease first, and then you will have to increase. Okay, so I hope that explains your relative and local maximums, your intervals of increasing and decreasing. Again, we're working on our parent functions and getting you to know these characteristics, so I'll be posting the characteristics worksheet. And on that worksheet, I will ask you questions, and it could very well be that the answer is none. Okay, so for example, if we looked at the line y is equal to x, or negative x, let's say that's our function. Okay, that is the 45-degree line with the slope of negative 1. Okay. So if I asked you about the intervals where it increased, well, this is a decreasing line, so there are no intervals of increasing and decreasing. Okay, so none is a perfectly acceptable answer on that worksheet. And another thing is, if we were looking about for the intervals of decreasing, well, it decreases for all real numbers because that's the domain. So sometimes we'll say that this decreases on its entire domain. Okay, so I think that should get you through. Send me an email if you have a question.